May 1972. The Cold War is not cold. Soviet Tu-95 Bear aircraft, nuclear-capable, long-range, relentless, are circling NATO convoys in the North Atlantic, identifying targets, feeding coordinates to submarines waiting beneath the surface, and the United States Navy has a problem: not enough carriers, not enough fighter cover, and not enough time to build them. The Soviets know this. They're counting on it. So the Pentagon does what it always does when backed into a corner. It bets everything on a machine that doesn't exist yet. A supersonic fighter that needs no runway, no carrier deck, no catapult. A jet that can lift straight off a small ship, anywhere on the ocean, intercept a Soviet Bear at Mach 2, and land vertically when it's done. On paper, it was the most capable naval fighter concept ever designed. In practice, it couldn't get off the ground, and the story of why is one of the most classified failures in American aviation history. To understand what the Navy was trying to build, you need to understand the threat it was trying to answer. By 1970, the Soviet Navy had transformed itself from a coastal defense force into a genuine blue water threat. Nuclear submarines, surface combatants, and, most dangerously, long-range maritime patrol aircraft. The Tupolev Tu-95 Bear, a massive propeller-driven Soviet bomber with intercontinental range capable of circling NATO convoys for hours, tracking them, photographing them, feeding targeting data to submarines running silent beneath the surface, and the US Navy couldn't stop them, not efficiently. Every intercept required a full carrier strike group, a nuclear-powered supercarrier worth $5 billion, plus its escort ships, deployed to chase a single Soviet reconnaissance aircraft. The math was simple. The Soviets could generate more bears than America could generate carrier groups. That's when Admiral Elmo Zumwalt, the youngest chief of naval operations in history, put a classified plan on the table. He called it the high-low concept. Instead of relying exclusively on massive supercarriers, the Navy would field a new class of small, fast, affordable ships. The Sea Control Ship, 670 feet long, costing $100 million each, 1/8 the price of a full carrier. 8 of them were planned, each one carrying 14 helicopters and a small squadron of high-performance supersonic VTOL fighters. Fighters that could launch vertically, intercept anything the Soviets sent, and recover without a runway. Fighters that, as of 1972, did not yet exist. In December of 1971, the Navy issued the requirement: supersonic, VTOL-capable, AIM-7 Sparrow missiles for beyond visual range engagement, a full radar system, performance exceeding the F-4 Phantom, but able to operate from a ship 1/8 the size of a supercarrier. 4 companies responded, 2 designs made the final cut. Convair put forward a conventional approach, functional, conservative, proven principles. Rockwell International went the other direction entirely. Their proposal, the XF-12A, was unlike anything the Navy had ever seen. A sleek, futuristic aircraft with a pronounced delta wing set far back on the fuselage and forward canards. Single engine, single seat, built for Mach 2 performance. And the VTOL system was genius on paper. Instead of separate lift engines, which would add weight and drag, Rockwell's engineers designed the entire wing to become a lift device. The engine's exhaust would be diverted through an internal ducting system into a series of thrust augmenters, essentially Venetian blind-style nozzles built directly into the wing and canard surfaces. At the flip of a switch, the wings wouldn't generate aerodynamic lift. They'd generate jet thrust, straight down. The aircraft would rise off the deck on columns of superheated air pushed directly through its own wing structure. Rockwell called it the thrust-augmented wing. The Navy called it exactly what they needed. In May of 1972, Rockwell received a $47 million contract for 2 prototypes. The XF-12A was officially born, but something was already wrong, and the people running the program knew it. NASA ran early wind tunnel studies on the thrust augmentation concept. The results came back troubling. The vertical lift figures Rockwell had promised, or the numbers the Navy had built their entire sea control ship concept around, were almost certainly too optimistic. The internal ducting created turbulence. The exhaust flow through the wing nozzles didn't behave the way the computer models predicted. There were corner flow anomalies the 1972 engineering tools simply couldn't diagnose. Computational fluid dynamics, the software that would have spotted the problem instantly, didn't exist yet. The program continued anyway. $47 million was already on the table. The Sea Control Ship was already in design. Admiral Zumwalt was already briefing Congress. The political momentum was too large to stop over a wind tunnel report that nobody wanted to believe. Ground testing began in 1974, and the results were worse than anyone had admitted publicly. The XF-12A had a 30,000-pound class afterburning turbofan engine, a Pratt & Whitney F401. It generated enough raw thrust to lift the aircraft's 20,000-pound empty weight. On paper, the math worked. In practice, it didn't. The engine made the thrust, but the ducting system that was supposed to channel that thrust into the wing nozzles was losing enormous amounts of energy in transit. Pressure drops, Flow separation. Turbulence in the internal passages. By the time the exhaust reached the wing surfaces, it had lost so much energy that the theoretical lift figures were simply not achievable. Rockwell's engineers modified the rear exhaust system, closed off the primary nozzle and rerouted everything into the wing augmenters, squeezed every possible pound of lift out of the system. It wasn't enough. The aircraft was tethered to a test rig, the engines were run at full power, the XFV-12A strained against its restraints, and it couldn't lift itself off the ground. A machine with an engine generating more thrust than its own weight could not hover. That sentence should not be physically possible, but it was true. By 1977, 5 years after the contract was signed, the first prototype was finally completed. It was, externally, a beautiful aircraft. Futuristic, aggressive, visually unlike anything in any Air Force on Earth. The nose assembly borrowed from the Douglas A-4 Skyhawk. The engine intakes taken directly from the F-4 Phantom. Parts from two legendary aircraft married into something entirely new. But beauty is not thrust, and the tethered test results had already told the story. The fundamental problem was irreversible without a complete redesign of the thrust augmentation system. The ducting that routed exhaust through the wings was generating losses that no modification could overcome within budget or timeline. Rockwell's own division chief engineer, Bob Gulcher, would later admit the brutal truth. Unfortunately, computational fluid dynamics was not available at the time. That may have predicted the corner flow for the ejectors and isolated the vertical thrust anomalies. In other words, they needed technology that wouldn't be invented for another decade to know the design wouldn't work. And they'd spent 5 years and $47 million finding that out the hard way. But the physics weren't even the worst part of this story. The program had already lost its reason to exist. Admiral Zumwalt, the architect of the sea control ship, the man whose vision the entire XFV-12A program was built to serve, had retired in 1974, and with him went the political will. The officers who replaced Zumwalt at the top of the Navy belonged to a different school of thought. Admiral Rickover's school, nuclear power, supercarriers, large, advanced, irreplaceable platforms, not cheap, distributed small ships designed to absorb losses. The sea control ship program was quietly strangled in committee. 8 ships had been planned, a prototype concept was demonstrated, preliminary contracts had gone to shipyards, all of it canceled. No sea control ships would ever be built, which meant the aircraft designed specifically to fly from them was now a supersonic VTOL fighter without a ship to fly from. The XFV-12A had lost its mission before it ever flew. The Navy still had options. The British had already solved the VTOL carrier fighter problem with the Hawker Siddeley Harrier. Subsonic, limited range, not supersonic. But it worked. It actually worked. It could take off vertically, it could land vertically, it could fight, and in a move that was genuinely unprecedented. The United States Marine Corps adopted a foreign frontline combat aircraft into American service. The AV-8A Harrier, British-built, American-operated, flying from American ships. The same Navy that had spent $47 million trying to build a better American solution had quietly acknowledged by accepting the Harrier that the British had won this race. Rockwell kept trying. Engineers proposed modifications to the XFV-12A. Not a full VTOL fighter, maybe a short takeoff and vertical landing variant. Some officers noted privately that the aircraft, stripped of its problematic vertical thrust requirement and flown in conventional or short takeoff modes, might have made an exceptional combat aircraft. Gulcher himself said it clearly. Had we shifted away from vertical lift, I believe the aircraft would have made an excellent short takeoff and vertical land fighter. But the Navy wasn't interested in a consolation prize. In 1981, 9 years after the contract was signed, the XFV-12A program was officially canceled. 1 completed prototype, 1 partially built, 0 conventional flights, 0 VTOL demonstrations, 0 combat potential. The second prototype was scrapped. The first was disassembled. The cockpit section was eventually stored at NASA's Plum Brook Station in Sandusky, Ohio, where, as of 2012, a group of high school students were restoring it as a museum exhibit, a 9-year program, $47 million. The highest performing paper specification of any naval fighter concept of its era, restored by high school students. But here's what the failure actually proved. The Navy's instinct was correct. The threat was real. Soviet bears were real. The convoy vulnerability was real. The need for distributed, affordable, VTOL-capable naval air power was not a fantasy. It was a genuine operational requirement. The XFV-12A didn't fail because the idea was wrong. It failed because the specific technology required to make the thrust-augmented wing work, precise computational fluid dynamics modeling, didn't exist in 1972 when the contract was signed. Rockwell built something their era couldn't validate, and the Navy canceled it before anyone figured out whether a different approach might have worked. The Harrier filled the gap, subsonic, limited, but real. And then 30 years later, Lockheed Martin started building the F-35B, a supersonic 5th-generation stealth fighter with a shaft-driven lift fan capable of short takeoff and vertical landing. operating from small amphibious assault ships. In 2013, the F-35B achieved full operational capability with the U.S. Marine Corps. Everything the XF-V-12A was supposed to be, just 30 years later and 3 generations of technology further down the road. The Navy's vision in 1972 was correct. The hardware simply wasn't ready for the vision yet. The cockpit section of the XF-V-12A sits in Ohio. The F-35B flies off ships around the world every day, and somewhere in that distance, between a museum restoration project and the most advanced fighter on the planet, is the real story of what America's vertical takeoff fighter program actually was, not a failure. A first attempt, expensive, painful, canceled before it ever flew. But the first attempt at something that the entire world now takes for granted. A supersonic fighter that needs no runway, no catapult, and no supercarrier. The XF-V-12A didn't build the future. It just got there too early to survive it. If you want more stories about the programs the Pentagon built, killed, and quietly resurrected 20 years later, subscribe. New episodes every week, and drop it in the comments. If the thrust-augmented wing had worked, would the F-35B even exist? Or would Rockwell's design have beaten it to the flight deck by 3 decades? Every comment gets read. See you in the next one.